when you do wolfram alpha, and do a determinant, you get a picture. Okay? The picture for this standard SD model, okay, the 0.9, 0.8, 0.1, 0.9, 0.2, 0.1, 0.8, is consistent with this picture, okay? In that, what happens if you map this vector? Well, the first thing you do is it maps along this line to a vector that's 70% of the distance from here, as we've seen. In other words, it maps to this vector. So, we got this vector, right? And this vector maps to this one. Now, I don't have these right. This one rotates less than this one does. I didn't draw it. I offered to do an exact replica, and y'all acted skeptical, and I lost my confidence, so I didn't do it. Okay. Okay, but you get something like this, right? Okay? Now, it shouldn't be hard to convince you that any vector along this axis is going to map to a vector along the same direction as this one. Yeah, if it's twice as long, it'll map to a vector twice as long, but it's always going to map on the same line, right? So in that sense, your horizontal axis maps to an axis in this direction. So it's like you have a whole new axis. Okay? And your vertical axis maps to an axis in this direction. So it's like you've taken your axes and squeezed them together a little bit. Okay? Of course, out in this quadrant, or what was this quadrant, things have moved apart a little bit, right? In transformations in general, for stochastic matrices, 2 by 2 matrices, everything important happens in the first quadrant, okay? All your vectors will stay in the first quadrant. Okay, but in general, they can change quadrants, they can rotate, they can invert, and when you go into 3 dimensions, it gets to be even more fun, to the extent that it's really, really hard. And you usually don't do that whole analysis in linear algebra class. Use linear algebra as a basis for understanding groups of rotation matrices, which is a pretty advanced topic, okay? Most undergraduates don't get to it until at least their junior year and often up to graduate school. Okay, so you got this picture anyhow. Do we understand this in terms of what we've seen here?
Yeah.
Okay? Okay, well, let's see. What would happen? And this thing isn't very well drawn to scale. This line is too steep, but you know, this point up here is not on this line, okay? And actually this line should be a lot lower. But if we did a vector from here to here, okay? Now that's the vector we get if we do this vector and then slap this one on it, right? In other words, we get here by doing this and this, right? Well, after it's transformed, what we get is what we get if we do this and then this, okay? So this point would transform over to here, okay? And this is a square, right? Okay, well that means that this square maps to this parallelogram. Okay, you're distorting space. Okay, so if you take a picture of somebody and you want to make them look kind of funny, you just apply this transformation to that picture, take every pixel and move it according to this rule, just multiply by this matrix, very easy to do if you know a little programming. I mean, very little. Okay, it's like 2 lines, okay? And you can make them look a little bit funny, okay? Make sense? Okay? So, you know, you take this picture. What are your friends, right? What's it going to end up looking like? Well, it's going to end up looking kind of like this. maybe it's not that funny, but if you do it with facial features, you know, it gets better. Again, let me draw some good facial features in here. Okay? Now think about what that would look like. That's a pretty detailed picture of a typical human face, isn't it?
Yeah.
I am kind of proud of my artistic ability. Okay. Well, that aside, think about that. We don't have time to do a whole lot with transformations like that. We've gone way deeper into this than I've ever been able to before, but that's because y'all are doing really well with it, okay? So when you see this picture, which is what you see right here, okay? That's what you're seeing. You're seeing how the unit square gets distorted, okay? And then we can also say that the area ratio is equal to the determinant. Would not be hard to prove, but we're not going to have time because we only got a couple more days here. Okay? Doesn't mean I wouldn't give you some hints and ask you to do it on the exam. Because you're right at the point where you can do that if you're on top of things. And don't worry, I'm not going to ask everybody, not all the questions would be that challenging, okay? I'll ask you some easy questions too. So don't worry about it. That'd be one of those questions I say prove it, and I would think at least a couple people would be able to prove it, and I would be able to tell who, okay? Several would equally seem equally capable of doing that. So whoever hits it right, maybe everybody does. I don't know. So when we get the exam, you can expect questions that build on the questions we have and use the knowledge you've gained by doing the work. Okay? But they're also straightforward questions. Okay? So don't be paranoid. Everybody's going to do okay. And I think the average is going to be quite high. Like on my exams, 40% is a really high average.
No.
So don't expect to be making 90s, but if you do, that's great.
Oh my.
Okay? I've got a story that goes with that too, but I won't do it on camera. Not that it's not something I would put on camera, except there's a pretty famous person involved in it. Okay. I mean, not anybody you've heard of, but somebody whose picture was on Sports Illustrated 5 times, I think. Okay? Happened to be one of my professors. And an NFL championship quarterback. Okay. Interesting guy. Okay. That's more than I wanted to say. Anyhow, when you see this picture, you'll know what it means. And there's another thing, since I'm talking about what the determinant means. Okay, if you go from here to here to here to here and back, how do you go here? Well, clearly you go from here to here to here to here to here, right? Mm-hmm. In other words, counterclockwise is counterclockwise here, right? If the determinant is negative, that gets reversed. Clockwise and counterclockwise reversed. Okay? Yeah.
This might be a dumb question, but what is the difference between a determinant and an eigenvalue?
You take the determinant of this, set it equal to 0, and lambda is your eigenvalues, okay?
Okay.
So this gives you the characteristic equation. So as we wrote down earlier, the determinant of this is this times this minus this times this. which is this. So determinant equals 0 is this equals 0, it gives you these. You plug these back into one of the equations and you get your eigenvectors. Okay?
So it's just a coincidence that the determinant and the eigenvalues are equal for this one, or is that normal?
I don't know. I haven't proven it. Okay, yeah, question. There's an open question right now. And I'm not going to prove it. I'm going to put this in the exam. Okay? Yeah, another one of those questions that, you know, if you don't get it, it's probably not going to hurt you, but if you do, you get to put another feather in your cap pretty soon. You'll be an American Indian chief. Okay? Okay. And for this model, now the determinant of the matrix itself, without the eigenvalues, is 0.7, right? Now the determinant of this matrix, for the reasons that I went over just a while ago, is what you use to get your characteristic equation. This is the determinant of the matrix itself, and which is what I did up there. I didn't have any lambdas in that thing. Okay? We notice that the determinant of the matrix is 0.7. Also, that lambda is one of our eigenvalues is 0.7, right? Is that always going to happen?
Yeah.
Well, how would you answer that question?
By solving every single entry.
That's 11, I hope, because that's 14. I've got less than a second, and I'm, oh man, that can't be. Okay, that's 12, not 17. It wouldn't have gone from 14 to 17 anyway, would it? Minutes. Okay. I don't have much time, so. I don't want to have to split this video, it just takes forever. Confuses everything. So, if you've got R1 minus S, 1 minus RS, with R and S both between 0 and 1, as we've seen, right? Is the determinant of this thing an eigenvalue. Okay? That's how I will phrase the question. So if you come in here knowing how to solve that problem, and I forget to put the question on the exam, you can write it down and write out your solution and you get credit. Okay? Another thing on the exam, there will be problems of this nature that you get credit for, but you don't get penalized for. Okay? If you don't get it, okay, you didn't get it. But if you do get it, typically I'll say, okay, yeah, you got 10 points in this problem, and I'll replace the next lowest problem on the test with your solution, with the 10 points. Or if you get 8 points and it helps your grade. Make sense? Run out of time here.